Hello and welcome once again to our series on mathematics. We are going to look at a popular topic known as algebraic expressions in this lesson. Assuming today Amma has 5 Ghana cedis, another time she has 7 Ghana cedis, another time she has 1 Ghana cedis, and at another time she has 10 Ghana cedis. You can see that at different times Amma has different amounts of money. In mathematics, we can use what we call a variable to represent the value that Amma has each time. So we can say at any point in time Amma has X Ghana cedis. The use of the letter is what we call the variable. This concept is what we are going to look at today in this lesson. We are going to look at what algebra is. Algebra involves the use of alphabets and other symbols to represent numbers in mathematics. For example, I can say I have 3 today and I have 5 tomorrow. So I can use the letter X to represent those values. There are 2 main types of symbols that are used, namely the variable and the constant. Let's look at some examples of variables. Let's say I have X plus 5 being equal to 8. That means the X value is 3, because when I add 3 to 5, I will get 8. At another time, I can decide to change the X value to 2, and that will give me a sum of 7 when added to the 5. So you can see that the X value can change at any time. That means when we use variables, we are only using them to refer to changing values. We may also have X plus Y being equal to 7. At one time, I may decide that X is 2 and Y is 5. So this gives me a total of 7. Another time, I may change the value of X to 6 and the value of Y to 1. And this will still give me a total of 7. Let's now look at constants. Let's say we are adding 4 to a constant which is represented by this symbol, which is known as pi. The answer will be 7.142. That means the value of pi is 3.142. So when we even add it to 3, we are going to get 6.142. When we change the first value, the total sum will change. You can see that the pi value does not change. It is always 3.142. This use of symbols to represent unchanging values is what we call constants. So what do we mean by algebraic expressions? These are expressions that involve variables, as we saw earlier, but also they include mathematical operations such as addition, subtraction, multiplication, and division. For example, I can write an expression such as X plus 5. This is an algebraic expression because it involves the use of a variable. We can also have 15 minus m, which involves a subtraction and as well as a variable. We may also have 2 times a. We may also have 4y divided by 7. Let's try and relate a bit more to the parts of an algebraic expression. This is a complete algebraic expression. It has 3 terms. A term in algebraic expressions is separated by any of the operation signs like plus or minus. So we can say in this algebraic expression, we have the first term being 2x, and the second term is separated by the plus sign, which gives us 5y. This is also a term. Then the third term is the last one on the right hand side. So as we said, each term is separated by the operation signs. Let's look at a bit more. As we said earlier, we can have a term which is separated by an operation sign. For example, we have 2x squared. And we can also have 5x. Let us concentrate on the first one. We have 2x raised to the power 2. The 2 over here, which is written near the variable x, is what we call the coefficient. So we can say 2 is the coefficient of x squared. For the second term, we have negative 5x, as you can see. Negative 5 is the value that is written by the variable. So we say negative 5 is the coefficient of x. Note that this time we did not say x squared. This means the coefficient is the number that is written before the variable or the alphabet used in the algebraic expression. Let us look at what we mean by the like terms of an algebraic expression. The like term refers to the terms of an algebraic expression that has similar structure regardless of the coefficients. For example, if I have 5x and 7x and negative 2x, you can see that even though the coefficients are different, the variables are the same. This means they are like terms. We may also have a more complex one like 2x squared and 8x squared. You can see that the variable has a square on it in each case. This is different from just writing the x. Even though we have the coefficients changing, the variable together with its power is not changing. So we can say these are also like terms. We can also have like terms like 3x cubed and x cubed. This means the coefficients are different, which is 3 and 1, but the variable together with its power remains the same. Let us see how we can identify like terms. First of all, the variables must be the same. For example, if we have 2x squared and 8x squared, you can see that the variables are the same. We have x and not x and any other thing. This means they both have the same variable. The second rule is that the powers of the variable must also be the same. In this instance, you can see that they both have powers of 2 appended to the variable. This means the two are the same in terms of likeness, even though their coefficients are different. Let's look at another example. Assuming we have 2x squared and 8x cubed. As we said, the variables must be the same. We can see that the variables in this case is x, which satisfies our first condition. But for the second one, it says the powers of the variables must also be the same. But for our example, we can see that we have 2 and 3, and these are not equal. So we can say that these two are not like terms. Composing algebraic expressions can really be fun. Let us see a few steps of how we can do this. For example, if we have the variable x and we want to add the number 3 to it, we can say x plus 3. This means we are adding a number to the variable. In another case, we may decide to write the number first. So for example, we may have 7 and we are adding the variable a to it. Sometimes we may add a variable to another variable. For example, if we have a variable a, we may decide to add another variable b to it. So whatever numbers we have, we just substitute and work it out. What if we are taking a number from a variable? This is also simple. Taking the number means we are subtracting. So if we have a variable x, we can subtract 3 from it. Sometimes we may want to take the variable out of a given number. For example, if you have 9 as the given number, you may decide to take a variable p from it. Also, you may decide to take one variable from another variable. For example, if I have the variable a, I may decide to subtract the variable b from it. We may also decide to multiply a variable by a given number. For example, if I have this variable x, I may decide to multiply it 3 times. So I may have times 3, and this will give me 3x. Another example is having the variable a squared. I may decide to multiply this by 5, and this will give me 5a squared. We can also multiply a variable by another variable. So we may have x and multiply it by another variable, say y, and this will give us xy. For division, it's also simple. We may decide to divide a variable by a number. For example, we are dividing this variable x by 2. That means we are finding half of the variable. We may decide to divide the variable b by 3. That means we are taking a third of the variable b. We may decide to divide it by 5. That means we are taking a fifth of the variable. We have just seen the basics of how to compose or form algebraic expressions. Now let us go through a few examples to see how we can write algebraic expressions in compound forms. Look at this example. It says a number is subtracted from 6 and the result is multiplied by 3. The first part of this sentence says there is a number which has not been given. So what we can do is to give a variable to this unknown number. For example, we may decide to use x to represent that number. That is the first step. Then the second part says the number is subtracted from 6. That means we will do 6 minus the variable. So we will do 6 minus x. And then it is said that the result of this subtraction is multiplied by 3. So we will have 3 into bracket 6 minus x. This is very simple. From just one statement or one sentence that has been given, we have been able to form a very nice algebraic expression. In this second example, we have been told that the square of a certain number, which is unknown, is added to 5 times the number, and the result is added to 3. This one looks very difficult, but we can take it one by one and we will compose the algebraic expression out of it. The first thing we have to do is to find a variable to represent that unknown number. We can decide to use our common variable x. Now it says in the first part that the square of that unknown number is added to 5 times the number. Before we continue, it says the square of that number. What is the square of x? It is x squared, right? So we have done part 2. And we are being told that it is added to 5 times that same unknown number. 5 times that number means 5 times x. And we are adding the x squared to it. So we will have x squared plus 5x. Now the last part says the result is added to 3. So everything we had in step 3 is going to be added to the number 3. And this will give us x squared plus 5x plus 3. Was this not so simple? If you look very carefully and take care, you will definitely arrive at the algebraic expression required. Let's look at one more. We are being told that Amma has 3 points more than Kofi's points. The product of their points is 40. So we are expected to write an algebraic expression for this. Let's assume we don't know Ahmed's points because we have not been given Ahmed's point. We have only been given the difference between Ahmed's point and Kofi's point. So we are going to assume that Ahmed's point is represented by the variable a. And we are going to use k to represent Kofi's points. We are being told that Amma has 3 more points than Kofi's points. This means whatever Kofi got, when we add 3 to it, we will get Ahmed's points. So we will have k, that is Kofi's point, being added to the 3 to find Ahmed's point, which is a. That was simple, right? Another part of this question stated that the product of their points is 40. So we know that product means multiplication. So when we multiply Ahmed's point by Kofi's point, we will have 40. In effect, we have been able to derive 2 solid statements based on this question. In this next section, we are going to look at open and closed statements as applied to algebraic expressions. In the English language, we make certain statements that are based on facts. For example, we can say that orange is a fruit. This is true, right? Orange indeed is not a vegetable, but indeed a fruit. We can say Mary is going to school, and many more. These are all based on facts. In mathematics too, we can make statements. For example, I can say 6 plus 4 is equal to 10. Is this true or not? This is indeed true because when we add 6 to 4, we will get 10. We can also say 9 is an odd number, and much more. These are examples of statements we can make in mathematics based on facts. There are two main types of statements. One is what we call closed statements, which means they are always true. There is no other option apart from it being true. We can also have open statements, statements that are not known to be true or false as at the time of making them. Let's look at a few examples of closed and open statements. We start with closed statements. We can say 2 is an even number. This statement is always true, right? We can also say 2 is an odd number, but we know that 2 is not an odd number, but an even number. So the statement that 2 is an odd number is always false. This means it is closed. Let's have some more mathematical examples. Let's say we have 11 plus 3 being equal to 14. This statement is always true. But if we do 11 plus 3 being equal to 17, you know that this statement is always false. Let's look at some examples of open statements. I can say n is an even number. We can say the statement is true or false, depending on the value of n at the time. For example, if I say n is equal to 2, it means this statement is true. At another time, if I say n is equal to 5, 5 is an odd number, so this statement will be false as at the time. Let's assume we also have n plus 5 is equal to 8. This statement will be true or false depending on the value of n at the time. If the value of n is 3 at the time, it means we will have 3 plus 5, which is equal to 8. And so this statement will be true. But if it has a different value, let's say 2, we will have 2 plus 5 being equal to 7, and this is not equal to 8. So we can say the statement will be false at the time. Let's go a bit further into open statements. Let's assume we have x is greater than 3. What does this mean? It means we can have several values that are greater than 3. For example, if we have a range or a domain, as we call it, and we say x is such that x is equal to 2, 3, 4, 5, and 6. You remember this set notation from our lesson on set. When we look at the condition we have been given, it is said that x is greater than 3. We are going to use the values in the set to replace the x and check for the conditions to see whether they are true or false. We start with 2. We are going to write 2 is greater than 3 because that is how the x is greater than 3 has been written. But is 2 greater than 3? No, 2 is actually less than 3. So this statement that we have made is false. Let's look at the next one, which is 3. We will have 3 is greater than 3. 3 is not greater than 3, but rather equal to 3. So this statement we have just written is also false. Let's look at the next ones. We will have 4, 5, and 6. 4 is greater than 3 is true because indeed 4 is greater than 3. The same thing applies for 5 is greater than 3, which is greater than 3 indeed. And we also have 6 is greater than 3, which is true. We can test for truth sets based on this. Let's now delve into operations that involve algebraic expressions. We are going to look at addition and subtraction, as well as multiplication and division. We start with addition and subtraction. Addition and subtraction of algebraic expressions can work if we have like terms. For example, if I have x plus x, it means x and x are like terms. I hope you remember what we mean by like terms. It means the variable must be the same in terms of the letter used as well as the power or exponent attached to it. X plus x can be rewritten as 1x plus 1x. Normally, when we have 1 as the coefficient of a variable, we do not write it. We just write the variable straight away. 1x plus 1x will give us 2x. because we are going to add the coefficient and not the actual variable. So we will have 2x. Let's look at another example. Let's assume we have 2x plus 3x. As we said earlier, we will have to add only the coefficients of the variables if they are like terms. So this will give us 5x because we will add the 2 and 3 to give us 5, and we maintain the variable as 1. Let's look at an example involving subtraction. Let's assume we have 7x minus 5x. Once again, only the coefficients are considered if they are like terms. So we are going to do our operation on the coefficient. So we will have 7 minus 5, which is 2. So we will have 2x because we will append the variable as well. We are now going to look at the grouping of 2 or more like variables. If let's say we have a complex algebraic expression like this, you can see that we have 2 like terms here, which is 2x and then 4x. And then for the remaining ones, we also have another set of like terms, which is 9y and 4y. We can group the like terms together before computing them. This is a good mathematical method or approach because it allows you to do your things in an organized way. We will group the like terms which have x as the variable together as 2x plus 4x, and we also group the terms which have the variable y separately. So we will have 9y minus 4y. Note that when we move them, we have to move them together with their signs or operation signs that precede them. Having done this grouping, we can then go ahead to simplify the expression. We will have 2x plus 4x being done separately because they are like terms. So we will have 2x plus 4x being equal to 6x. Then for 9y minus 4y, we will have 5y. So our final answer will be 6x plus 5y. Let's look at a more complex example. We have 5x squared plus 3x plus 4x minus 2x squared. Let's use the grouping of like terms approach to simplify this. You can see that we have 5x. You can see that we have 5x squared and negative 2x squared as like terms. So we can write them together. And we also have 3x plus 4x as like terms separately. So as you can see, these are like terms, so we can work them together. 5x squared minus 2x squared will give us 3x squared because we will only work with the coefficient and maintain the like variable. 3x plus 4x will give us 7x. So our final answer will become 3x squared plus 7x. Let's look at another example. We are going to group like terms of this question that we have been given. 2x squared does not have any similar like term, so we have to write it separately. If you watch carefully, you can see that we have xy and negative 3xy, so we can write these separately as well. Then we will have 5x plus 6x being another set of like terms, and then we will have negative 4 being the last term. Since the x squared does not have any accompanying like term, we just leave it as it is, so we will have 2x squared. But for the first set of like terms, we will have 1 minus 3, which will give us negative 2. Then we will append the xy to give us negative 2xy. And then we will also work out the other set of like terms, which is 5x plus 6x to give us 11x. So our final answer will become 2x squared minus 2xy plus 11x minus 4. We now delve into multiplication and division involving algebraic expressions. In multiplication of algebraic expressions, we can easily join two variables. We can work out their coefficients separately, and we can also work out the variables separately. Note that if we have like terms, this is what will happen. We will have x times x. For example, x times x can be written as x raised to the power 1 times x raised to the power 1. Have you seen anything familiar with this? These include powers that we are going to compute on. I hope you remember when we studied about indices and how we used to compute this. According to the law of indices, we have to add the exponent if we are multiplying and maintain the base as one variable. So we will have x raised to the power 1 plus 1. And so this will give us x raised to the power 2. We can also multiply two variables that are not the same. For example, if we have x times y, this will simply give us xy. But what if they have coefficients that are greater than 1? For example, if we have 2x times 3y, we have to multiply the coefficients separately. So we will multiply 2 and 3 separately to give us 6, and we will also multiply the x and y to give us xy. So this will give us 6xy. Let's look at a few examples of this. We've been asked to simplify this expression, 5x squared times 3x. We can rewrite this as 5x squared times 3x raised to the power 1. When we multiply the coefficients 5 and 3, we will get 15. And when we maintain the base of the variables, that is x, we will have to add the exponents, that is 2 and 1, to give us 3. So we will have 15x raised to the power 2 plus 1. And this will give us 15x raised to the power 3. Let's do another one. We have 2a times 8b plus 3ab. We simply have to multiply the first two terms by considering the coefficients, that is 2 and 8. When we multiply these two values, it will give us 16. And when we multiply the a and b, we will have ab. So this gives us 16ab. We are also being asked to add 3ab. So this will give us a total of 19ab. Very simple, right? Sometimes we may decide to do a multiplication of variables involving fractions. Let's assume we have x over y times a over b. When we have such fractions, what we do is to multiply the numerator parts separately and then the denominator terms also separately. That is, we will consider the items or terms at the top, and we will also consider the terms at the bottom separately and multiply them. So this will give us x times a over y times b, which will give us ax over by. Let's look at an example. We have been asked to simplify 2x over 7a times 3y over b. As we mentioned earlier, we multiply the numerator parts separately, and we also multiply the denominator parts separately. So this will give us 2x times 3y divided by 7a times b, and this will give us 6xy over 7ab. Let's look at another example. We've been asked to simplify 12x cubed divided by 7a times 3x squared divided by 4b cubed. When we multiply the numerator parts and denominators separately, we will have 12x cubed times 3x squared divided by 7a times 4b cubed. You can see that at the top part we have the bases being the same, that is x and x. So according to the law of indices, we can consider this. We will have to maintain the variable as 1, and then we will add the exponents or the powers. So first of all, when we multiply the coefficients 12 and 3, we will have 36. Then for the x, we maintain it and add the powers. At the bottom, we will have 7a times 4b cubed. This can be multiplied straight away. The top part will now give us 36x raised to the power 5, and the bottom part is now 28ab cubed. Let's now look at the division of algebraic expressions. Let's assume we have x raised to the power 3 divided by another x. According to the law of indices, when the bases are the same, we have to subtract the exponent from each other. But first of all, let's convert x to x raised to the power 1. So by subtraction, we maintain the variable and then subtract 1 from 3. And this will give us x raised to the power 2. If the bases are not the same, we can simply work out the value that this will give us. We do not need to do anything extraordinary. Let's look at one that involves coefficients that are greater than 1. For example, I have 10x divided by 2x. I'm going to consider the coefficients and work them separately, and that will give me 10 divided by 2, which is 5, before I write the variable appended to it. Let's look at a few examples. We've been asked to simplify the expression a raised to the power 7 divided by a raised to the power 5. Since the bases are the same, we maintain the variable as 1 and then subtract 5 from 7. And this should give us a raised to the power 2. Let's look at another example. We have 9ab raised to the power 4 divided by 3b cubed. We've been asked to simplify this. We can work out the coefficients of each term separately and then consider the bases or the variables as well. The coefficient of the numerator is 9 and the coefficient of the denominator is 3. 3 can go into itself once and go into 9 3 times. So we will have 3ab raised to the power 4 divided by b cubed. You can see that we have two of the variables having the same base, that is b. So since they have the same base, we can use the law of indices approach to subtract the lower one from the bigger one, or we subtract the power of the denominator from the power of the numerator. So this should give us 3ab raised to the power 4 minus 3, and this should give us 3ab raised to the power 1, which can also be written as 3ab. We are now going to look at an interesting aspect of algebraic expressions, which is called the removal of brackets. Removing brackets simply means we are going to expand on a group operation. For example, if I have a into bracket b plus c, and I've been told to remove the brackets from this, it means I'm going to expand the expression. What we have to do is to multiply the term outside the bracket by each of the terms in the bracket. We also have to maintain the operation sign during this time. Note that outside the bracket we do not have a plus or a minus, but we just have a. This is the same as a times into bracket b plus c. Let's now open this expression up. We start by considering a times b, and we also multiply a times c separately. So this will give us a times b plus a times c, which will give us ab plus ac. Let's look at an example involving this. We've been asked to simplify the expression 4 into bracket 7a plus 2c. We multiply the 4 by the 7a to give us 4 times 7a, and then we bring our plus sign, which is coming from the grouped operation, and then we will multiply 4 by 2c to give us 4 times 2c. 4 times 7a will give us 28a, and 4 times 2c will give us 8c. So our final answer will be 28a plus 8c. Let's do another one. We have negative 3 into bracket 3x plus 8y. We multiply the negative 3 by 3x to give us negative 3 times 3x. We bring our plus sign, and then we do the multiplication for the other term, which is negative 3 times 8y, and this should give us negative 3 times 8y. We are only bringing this bracket again because we want the negative sign to stand out from the plus sign. Negative 3 times 3x will give us 9x. We bring our plus sign again, and we will have negative 3 times 8y, which will give us negative 24y. This can be rewritten as negative 9x minus 4y. Let's look at a third example. We have 5p into bracket 2p minus 3q. We start by multiplying 5p by 2p, and that will give us 5p times 2p. Then watch very carefully. We bring a plus sign again, even though there is a minus in there. But this time we are going to multiply 5p by negative 3q. So we will have 5p times negative 3q. 5p times 2p will give us 10p squared. And then we will have our plus sign, and then we will have 5p times negative 3q, which will give us negative 15pq. We can rewrite this as 10p squared minus 15pq. All that we have seen so far involves the use of a factor to multiply one grouped bracket. We can also multiply two sets of brackets. For example, we have into bracket a plus b multiplying the whole of into bracket c plus d. To expand this bracket, we have to multiply each of the items in the first group by each of the items in the second group. That is, we will do a times c, and we will also do a times d. And this should give us a times c plus a times d. Then we will consider the second term, which is b, and multiply it by each of the items in the second group. So we will have b times c being added to b times d, and this should give us b times c plus b times d. Let's look at some examples involving this. We have into bracket a plus 3b being multiplied by 7a plus 2c. To do this, as we saw earlier, we consider the a first, and we will multiply it by 7a, and we will also multiply it by 2c. So we will have a times 7a plus a times 2c, and we will also have 3b times 2c. So this will give us 3b times 7a plus 3b times 2c. We can now work each of these pairs separately. We will have a times 7a, which will give us 7a squared. We will also have a times 2c, which will give us 2ac. Then we will add it to 3b times 7a, which will give us 21ab. And we'll also have 3b times 2c, which will give us 6bc. This represents our final answer for the expression. We are now going to look at some common expansion forms. Let's assume we have these two grouped operations. We have one involving an addition of two variables, and we also have one involving the subtraction of two variables. And all these are in two groups which are being multiplied or expanded by each other. Let's see what will happen when we solve this. We will have a times a, and we will also have a times negative b. So this will give us a times a plus a times negative b. Then for the remaining one, we will have b times a, and we will also have b times negative b. So this is what we will have. Now, when we watch carefully, we can simplify this. A times a will give us a squared. A times negative b will give us negative ab. B times a will also be ba or ab. And for the last one, we will have b times negative b, which will give us negative b squared. In the middle, we will have negative ab plus ab, which can also be written as ab minus ab. So these two can cancel out because it will give us a value of 0. So what are we left with? We are left with a squared minus b squared, and this is what we will have. So let's look at a practical example involving this. You can see that we have 3a plus 4 in one bracket, and we also have 3a minus 4 in another bracket. This means we have an addition in a separate bracket and we have a subtraction as well in a separate bracket, but all of them involve the same terms. So using the answer we got, we can decide to simply slot this in to find our final answer without having to do the long expansion. We know that this will give us a squared minus b squared, where a refers to the first term, which is 3a, and b refers to the second term, which is 4. So we will have 3a raised to the power 2 minus 4 squared, and this should give us our final answer, which is 9a squared minus 16. If you know this approach, or the difference of two squares as we call it, you do not have to go and do the long expansion, but simply just use this approach like it were a formula. Let's now look at the second one. This one says a plus b raised to the power 2. A plus b raised to the power 2 is in fact a plus b in one bracket being multiplied by a plus b in another bracket, right? The first one had a plus b being multiplied by a minus b, but in this case we are going to have a plus b and a plus b. We will now have to expand this by considering each of the terms as we have done earlier, and this is the long expression that we have. When we simplify this, we will have a squared plus ab plus ab plus b squared. AB plus AB in the middle will give us 2AB. So our final answer will become a squared plus 2AB plus b squared. Let's look at a typical example of this. We can see that the two operations in brackets are all involving the addition of variables. We can apply the perfect squares approach for this, where a will be regarded as 5x and then b will be regarded as 2y. So wherever we see a, we put 5x, and wherever we see b, we put 2y. And this is what we will have, a long expression. When we simplify this, we will have 25x squared plus 2 into bracket 10xy plus 4y squared. And this is our final answer. We can also expand perfect squares involving subtraction. That is, we are going to have a minus b all into brackets raised to the power 2. So when we write the long form, we will have into bracket a minus b being multiplied by another a minus b, which is also in brackets. We then have to consider each of the operations one by one, and this is what we will have as our answer. We can simplify this to give us a squared minus ab minus ab plus b squared. Minus ab minus ab will give us minus 2ab. So we will have a squared minus 2ab plus b squared. Let's look at an example involving this. This time our perfect squares involved subtraction. As we can see with the question, you can see that we have 5x minus 2y in both cases. There's a subtraction happening in each of the brackets. So we are going to use this approach to solve it. A in this case refers to 5x and b in this case refers to negative 2y. So we simply slot this in and work it out to arrive at 25x squared minus 20xy plus 4y squared. Let's now move on to what we call factorization of algebraic expression. A factor simply means writing out two common factors or more in an expression. What do we mean by this? Let's say we have two terms in an algebraic expression, which is AB plus AC. You can see that A is common to each of the terms. So what we normally do is to factor this out. This means A is a common factor. We normally do factorization if they are common variables, and also if there are common factors between the coefficients of the terms in the expression. Let's look at a typical example of this. We have been asked to factorize ax plus 2ay. We will have ax plus 2ay like this, and what we do is to consider the variables first. You can see that in each of the term a is common, so we simply factor it out and then write into brackets x plus 2y, which refers to the remaining items or variables and coefficients in the terms. Let's do another one. We have been asked to factorize 8ax plus 2ay. This time we can consider the coefficients first because we will have a highest common factor between the two, which is 2. So we have to write this separately outside the brackets we are going to introduce. But before that, let's look amongst the variables to see if they are common ones. Indeed, we have a, which is common to the two terms. So we now have a highest common factor of 2, and we also have a variable of a. So we put the 2 together to give us 2a, which we write outside the brackets. 2a can go into 8ax 4x times, and 2a can go into 2ay y times. As you can see, we are dividing through the original terms by the total factors that we got. Let's do another one. We have 25x raised to the power 3 minus 5ax squared. 25 and 5 have a common factor, and the highest common factor between the two is 5. Also, amongst the variables, x and x are common. But wait a minute, we have x raised to the power 3 and x raised to the power 2. We have to take the highest common factor between these ones as well. X raised to the power 2 can be found in x raised to the power 3 as well. So what we do is to write 5x raised to the power 2. The 5 outside refers to the highest common factor we found, and the x2 is the highest number of times the lowest one can go into the highest one. So we factor it out as well. 5x squared can go into 25x cubed 5x times, and when 5x squared goes into 25ax squared, it will cross out the 5 and cross out the x squared, so we'll be left with a. We have been asked to factorize this expression. This is a very long one. What we normally do is to spot two or more variables that have similar looking terms or variables in the terms. For example, for this one, we can see that ax and ac have something in common, so we can group them together, whilst by minus bm have something in common, so we also group them together. So in effect, we have rearranged the original question. This will help us do our factorization very easily. We can consider ax plus ac separately and factorize it, and we can also consider by and negative bm separately. The first part will give us a into brackets x plus c, whilst the second one has a common factor of b. So we factor it out and we write out the remaining, which is y minus m. We are now going to look at what we mean by quadratic expressions. A quadratic expression refers to an algebraic expression that involves 3 terms. For example, we may have ax squared plus bx plus c. The c over here is what we refer to as the constant. A typical example of this will be x squared plus 5x plus 3. You can see that in the quadratic expressions there are different levels of the variables in terms of the powers that they have. We normally have the highest power being 2. Let's now look at how we can factorize quadratic expressions as well. Let's assume we have x raised to the power 2 plus 5x plus 6. Solving for this can be very tricky, but let's take it one by one. To do this, we have to consider the constant value, which is 6. When I take two numbers and I multiply them, I have to find that value 6. For example, I may decide to take 6 and 1 and multiply them to give me 6. Now when I add 6 and 1, I must get the coefficient of x, which is 5. But when I add 6 and 1, I get 7. So I have to look for two different numbers. When I do -6 and -1, I get 6. But when I add these two numbers, I get -7, which is not the coefficient of x. If you watch the example, you can see that the coefficient of x is 5, and that is what we are looking for the second operation. So let's go for 2 times 3, which will give us 6. And when we add 2 and 3, we get 5, which is equal to the coefficient we are looking for. So we can assume that these two numbers, 2 and 3, are going to help us find the factors of this quadratic expression. Now that we have found 2 and 3 being equal to 5, that will help us break down the coefficient of x. So we are going to take the 2 and the 3 and use them to split the 5x, which will give us 2x plus 3x, as the two of them are equal to 5x. So we are going to take the 5, break it down, and we will have x squared plus 2x plus 3x plus 6. So having done this, we now have 4 terms in our quadratic expression, but we are going to simplify this in pairs. We are going to take the first pair, which is x squared plus 2x. When we simplify this, we will have x into brackets x plus 2. Then we take the second pair, which is 3x plus 6, and we factorize that one as well. The highest common factor of 3 and 6 is 3. So we are going to have 3 outside, and then we'll have the quotients, which are x plus 2. If you watch carefully, you can see that in each of the factorizations, we have x plus 2 and another x plus 2. So we are going to further factorize this separately. So we will write x plus 2 outside, and then we consider those factors that we got earlier, which is x and then plus 3. And then we put them together as well. So we will have x plus 3. This is how we factorize quadratic expressions. Let's look at an example of this. We have been asked to factorize x raised to the power 2 plus 6x plus 9. As we said earlier, we have to look for two numbers that when multiplied will give us the constant, and then when added will give us the coefficient of x, which is 6. These two numbers are 3 and 3. So we have to split 6x into 3x plus 3x. So this will give us x squared plus 3x plus 3x plus 9. We now factorize in pairs, and we will have x squared plus 3x being the first pair. When we factorize this, we will get x into brackets x plus 3. Then for the second pair, we will have 3x plus 9. When we factorize this, we know that the highest common factor of 3 and 9 is 3. So we write 3 out, and we'll get the quotient as x plus 3. The items in brackets are the same, so we factorize it out as x plus 3, and then we write the remaining x plus 3, which refers to the actual factors we got earlier, out separately. So we have factored this quadratic expression. Let's look at the last one. We have been asked to factorize 3x squared minus 2x minus 5. Before we continue, in the previous ones, we saw that we did not have any coefficient of the x squared. So we went ahead to use the constant as it was. But in this case, the coefficient of x squared is 3. So what we normally do is multiply that 3 by the constant to give us 15. So now the two numbers that we are going to look for must be multiplied to give us that negative 15. When we add those two numbers as well, we should get the coefficient of x, which is negative 2 as well. So the two numbers we are going to use are 3 and negative 5. When we multiply 3 by negative 5, we have the negative 15 we are looking for. And when we add 3 to negative 5, we are going to get negative 2. So we are going to use these two numbers, 3 and negative 5, to split the negative 2x. So this will now give us 3x squared plus 3x minus 5x minus 5. We then take the pairs we obtained to factorize this completely. We are going to consider the first pair and the second pair separately. The first one will give us 3x into brackets x plus 1, and the second one will give us negative 5 into brackets x plus 1. We factor out the x plus 1 because they are both in brackets and are the same, and we multiply this by 3x minus 5. This is our final answer. And also on this note, this brings us to the end of this lesson on algebraic expressions. I hope you have enjoyed it thoroughly. See you in the next lesson.